today's Princeton AI Alignment and Safety Seminar, or PASS. Today, we're honored to have Dr. Nathan Lambert with us for the talk. Nathan is a research scientist at the Allen Institute for AI, focusing on RLHF. Previously, he helped build an RLHF research team at Hugging Face. He received his PhD from the University of California, Berkeley, advised by Professor Christopher Pister, working at the intersection of machine learning and robotics. He was in Berkeley Autonomous Microsystems Lab and Roberto Calandra at Meta AI Research. He was an intern at Facebook AI and DeepMind during his PhD. Nathan was awarded the UC Berkeley CS Demetri Angelakos Memorial Achievement Award for altruism for his efforts to better community norms. We're excited to host Nathan here today, and we're excited to hear his sharing about Tulu 3, open source frontier model instruction and preference tuning. So without further ado, Nathan, please take it away.
Yeah, thanks, Lucy. Thanks for the invite and the wonderful intro. So yeah, as you can see, this is about Tulu 3, and there's preview here because not all of this is released yet. All the slides will have like preview results numbers, not final on them. But it's not that surprising that we're doing this, given that we've gone from Tulu to Tulu 2 to Tulu 2.5, and I'll kind of summarize what those were. And I'll kind of just get into it and explain the story of where things are and what we're trying to do. So a lot of people know this. This is just softballing. Language models, when they first are trained on tons of internet text, are very brittle or interesting or wild, whatever your term of choice. And they require some alignment or adaptation to downstream tasks. And this is primarily what we work on. We want to follow sets of prompts. You want to be aware of certain behaviors, toxic behaviors, and make the models actually better at tasks that deliver value. So we've been working on this for a while. Back before ChatGPT even, there's a lot of work on this vein where an RLHF pipeline would look something like this, where you do supervised fine-tuning, and then you create a reward model, and then you do something like PPO to do RLHF on top of this instruction-tuned baseline. The amount of data used is pretty small, so you can do like 10 to 100K data samples. This is kind of pipelines that we've been looking at for a while. Some of the earlier academic work and instruction tuning followed this with just scaling data up a bit. And this is what things looked like for a while. We kind of added DPO to the mix instead of PPO, but there wasn't that much changes in the overall system. So where this started with the Allen Institute was like Tulu 1 was the first major paper in this, which is just combining a bunch of open data sets that people had been making and just kind of see how you can mix instruction data sets to improve performance on a broad suite of tasks. This kind of naturally evolved with the whole DPO phase that was last fall, where Tulu 2 was our experiment of trying to train 70 billion parameter models with DPO and kind of add preference tuning to these pipelines. Ultra feedback was the data set that we used, and I'll talk more about that data set throughout the talk. Then Tulu 2.5 was us trying to get into this PPO realm and trying to understand where we should be using RL, kind of rather than just this easy to use direct preference optimization, and especially we continue to improve with instruction fine-tuning across a variety of tasks and taking data sets from different sources and kind of just plugging away. The biggest takeaway for PPO is that it actually consistently outperforms direct preference optimization, but it has a large implementation cost, and memory usage is about 4 times higher. We'll talk about the models that you use when you're actually doing RL later on, and throughput's just much slower because you have to actually generate tokens when you're training. For kind of a snapshot of what the performance looks like, we generally would take different SFT checkpoints and do preference tuning on varieties of open data sets, and we would do DPO and PPO and kind of hyperparameter tune all of them. And most of the time, no matter what we did, whatever data set we took for preference tuning, PPO would just be a little bit better across tasks that we care about. It's almost odd how consistent this was, and we just kept seeing that PPO is a bit better, but still that doesn't mean it's necessarily easier to work with. So if you're really trying to push your final model, it seems like PPO is the way to go, but DPO is just kind of the default starting point, and we still do that today. So this kind of lets us, like, you can see another important idea for Allen Institute is like, what is the state of open recipes for fine tuning? I think everyone knows what LM-Sys Chatbot Arena is at this point, the really popular kind of vibes or chat benchmark of both open weight and closed models. And it's taking off in 2024. But if you look at models that actually have open training data, you have to scroll all the way down to like position 66 or 74, which is pretty crazy. So we really need to, to develop new recipes built on open training data. So it became like a secondary large goal of this Tulu push when we're refreshing everything is like, why is there not, like, what is happening in the open data and open recipes for fine tuning out there? So the question is like, where to from here? We know that we could do things with instruction tuning. We know that DPO on datasets like ultra feedback works. We know this Instruct GPT learning to summarize pipeline pretty well, and we've replicated it. But like, what's happening in the bigger space of frontier model post-training, and is RLHF becoming more important? What is Llama doing? So like, how do we kind of adapt this diagram that I showed earlier to what we should do? So this is where we start, which is like what RLHF canonically looked like in the kind of core literature that defined it. But now if you look at something like Llama's report or the Nematron report, there's this really wild multi-stage, multi-optimization, many model checkpoints to get to the final instruction model. So here you can kind of see the core idea from these papers for especially Llama 3.1 and Nematron is that there are multiple rounds of preference tuning. So this is something that I was like, okay, I really want to try to have us understand why they're doing this when most of open models are training from completions from GPT-4 or whatever. We're really distilling from these big models where we see again and again from these closed labs that they're doing this multiple rounds of preference tuning. Specifically from the Llama report, you could see this prompt or this figure where they kind of do a combination of rejection sampling and DPO. So rejection sampling is using the supervised fine-tuning loss, but kind of filtering your data based on a reward model. And then DPO is how you integrate this pairwise preferences that they're getting from humans into an actual training function. And there's not a lot of details on the specific implementation of this giant mess, but I was really intrigued to see which parts of it we can reproduce in the open and kind of which parts of it will need further studying. And I think the Nematron paper from NVIDIA actually does do something really similar, but it's not talked about much in this vein, where they started with creating synthetic data, I think from the Mistral like 8x22B open weight model. And then they use that to kind of do this weak to strong alignment. And they talk a lot about iteratively improving their models until they got to this final Nematron 340B Instruct. And if you look in the academic literature or the code bases, there's just not really anything that shows us how to do this. So that was my major motivation, but there's a lot more specific questions we can go to. It's like, why are there no academic papers on rejection sampling? Like, does rejection sampling just not work in certain domains? Do we need bigger models? Do you need human data? Like, do we need to be spending the millions of dollars that Meta and NVIDIA can spend on human data? Oops. Like, how does one actually train a good reward model? I think earlier in 2024, this was much bigger of a question. Now there's actually a bunch of papers coming out that I'm happy to point people to where the entire paper is trying to understand the RLHF workflow from the reward model perspective and how to translate reward models into better models. But I would still say it's extremely early. I don't think that there's a settled recipe there either. Which of the many DPO variants that we've seen this year is actually the best? Like, should we just use vanilla DPO? Is that fine? How should we balance SFT and preference dataset sizes? I think if you look in Hugging Face, the common open instruction dataset sizes are like 1 to 5 million prompts, while ultra feedback, the state-of-the-art preference dataset, is about 60,000 prompts. Like that just seems like a fundamental misbalance of flops given the amount of tools in our repertoire. How important is on-policy preference data? I will talk about this one a lot. Like, how does Llama Instruct go up on MMLU? I think this is always a funny one, but it's like we don't really know what's going on when their base model has a lower score on things like MMLU, which is just really broad fractional knowledge, than an Instruct model, so on. But most of these things we'll discuss, but it's just kind of trying to bring clarity to every step in this process. And in order to actually do this and try to answer these questions relative to the previous Tulu models that I started with, we really needed to change a few things in our workflow. It really became a lot more work on creating new data sets rather than reusing data sets. So really only mixing data sets can go so far. It takes a lot of work to increase investment in preference tuning. It involves building a lot more tooling, just making things like DPO more efficient, scaling up LLM as a judge so you can take more prompts and build your own preference data sets, and then kind of decrease the mental focus on which algorithm is best mind space. I think You can look at the Tulu 2.5 paper where we show 1 point gains on PPO over DPO. But if you had just spent all that time improving data sets, you can see 5 to 10 point gains on the evals that you care about. So if the algorithm is just like 10% of the whole problem, you really need to spend more time on the data. And our biggest goal is to like create recipes for multi-capability language models. There's a lot of models that come out now that really are like, we see these evals like Arena Hard, Alpaca-Eval is the original MT bench, and there's growing more, which correlate really strongly with Chatbot Arena. But there are things that we want to use our language models for, and that closed labs are training the models to do, that Chatbot Arena kind of captures as a lower percentage of the overall ranking. These are things like code, math, precise instruction following. Like these are things that are underrepresented in Chatbot Arena, and therefore those other evaluations relative to kind of our interests and what language models are used for. And to be more specific, it's like we want to create an evaluation suite and we want to beat Llama 3.1 Instruct at a few sizes from the base model. So we want to kind of show that what these labs are doing can be completely opened up to the community and kind of built upon. So kind of a summary of the training process, which I'll then go through in more detail, and I'm sure answer more questions on, and then some of this will actually be updated before the final paper in a couple of weeks, but I think our general approach is likely to stay the same. So we take some base language models of interest. Mostly there's a Llama, but we're also taking our latest Olmo models, both from the past and ones coming soon. And then we train these kind of instruction tuning tech points. We needed to create new specific capability data. We're really wondering how much we should prioritize multi-turn chat data, and then also like try to get a reasonable answer on what we should do for safety, because closed models use extra small models to moderate their outputs for safety, but also we don't want to release a model that'll say the most flagrant and harmful things at the slightest prompting. So you kind of want to thread the needle of making the model useful, but also just making sure you're doing your due diligence on some level of safety. Then we do preference tuning, which looks like a standard variant of DPO on some new data sets that we're making and still using the same ultra feedback ideas. And then we're adding something new at the end, which we're calling ground truth reinforcement learning, which is we're using this kind of PPO setup to train exactly on prompts where there are verifiable answers to kind of improve evals like GSMAK, math, and IFFL. So I'm going to kind of go through these in order on what we're doing and give some insights into what the kind of specifics look like. But first, the kind of evaluation suite that we're doing, we're trying to be very principled on having a development and then a kind of unseen test eval set. So on this talk, I'm going to focus on these development tasks, which is things like MLU, GSMAK, math. IFFL is one that has showed up this year, which we find really interesting. And we have all of these unseen evals, and we haven't run them at all. We're actually still implementing our like true unseen eval set in our code base. So I don't have an answer exactly to how well our models generalize at this point, but you can see the trends on the development set. And we just think this is really important because most labs releasing Instruct models, especially that are closed, there's no way of really telling which evaluations they may have trained on and which they may have focused on. So we want to make this really clear so that the recipe can translate to other evaluations. So kind of the start of this is supervised fine-tuning. This is now a thing that people have seen many times in this kind of area of work. And the SFT design process is probably the more interesting thing. Is we've gone through tons of configurations for our models, and it's like, what are we actually doing? So at the start of the project, we mostly did this data mixing phase again, which is, okay, let's find new math data sets. That's where our numbers were low. Let's find new code data sets. Are there any good general instruction data sets we think we should include? And then we just try to mix them in with our Tulu 2 mix and see what goes up, what goes down. And then that's kind of like playing the game of how do you get numbers to go up and avoid second order effects. But then once we see that versus Llama 3.1 Instruct, we're still behind on certain numbers, is when we're like, okay, we need to create new data on math. So math is an example that I'll talk about because that's probably where most of the impactful creating new kind of specific data turned up. And when we actually look at the mix of what we have, it's kind of a mix of data sets that people know, and those are older ones like Open Assistant, Guanaco. is a pretty old mix. This has been what's one of the only human data sets that has been out there in the open for over a year now. The Guanaco mix is specifically the one that was released with the Q-Lura paper. We find FLAN to still be important for maintaining things like MLU and kind of big bench hard and the kind of basic NLP-ish reasoning tasks. And then no robots kind of rounds out, no robots and wild chat kind of round out the human data section. So it's interesting that in the end of the day, like a lot of our general capabilities chat came from human interactions, I guess, at least on the prompts. So wild chat is still completions with GPT-4. And you can see this like Tulu 3 hard-coded examples. This is just an upweighting so that the model knows that it was trained by OpenAI and not by, or knows that it was trained by the Allen Institute and not by OpenAI. Sorry, I got this backwards, but a lot of open models, if you ask them, will essentially say, I was trained by OpenAI to be a helpful assistant because everyone trains on GPT-4 outputs, which is still a problem and it's really annoying. But then you can kind of see as we get into these specific splits, there's a lot more kind of specific data that we created to generate specific evaluations. And if you sum these up, I think the total is about 1 million samples in this. And it's like you could go into each of these and look at examples for prompts and responses, which I don't have, just kind of tried to tell the story of this. But I think most of the innovation here and the impressive part of this is the generating new math data, which I continue on. So there was this paper that came out from a Tencent AI called Persona Hub. The title is really catchy. It's like scaling synthetic data to 1 billion personas. And this came out over the summer. And when I saw it, I was definitely like, wow, that is ridiculous, good clickbait title, but not something I ever expect to actually use. So what it is, what the original data set was a list of personas that were synthetically generated to kind of describe a type of person. And then with the persona, you could create a prompt that is like a math problem, but something that, say, a trucker or a forester would ask for. So if you're doing a moving company, then the math problem is going to ask about how many boxes, how much space you have, versus if you ask like an astronaut or a scientist for a problem, the math problem will be around physics or kind of like bodies in the solar system. So it's a really subtle change in what the kind of text of the problem is, while the distribution of the problems remains the same. And we were able to use this to great effect for math, where we think that generally this persona hub technique just gives us a bit of generalization so that the model can learn better from these synthetic completions that we're doing. So the actual completions is still pretty simple, which is we give the prompt we've created from the persona to something like the GPT-4 API and generate the completion. And we do a bit of filtering, but most of it is around prompt diversity rather than verifying the answers on the kind of outputs before doing SFT. And we applied these personas to multiple domains and saw consistent improvements in performance. And we can't say that we don't have a 100% answer that is due to this kind of generalization and diversity, but it really does seem like this. And I expect this technique to kind of keep scaling. There's some other sources of personas out there. I think Hugging Face team also created some personas that you can use to generate prompts. But it took me by surprise and gave us a lot of performance. I'll kind of get to the numbers later. What you actually do to the model looks like this. It's you like tell ChatGPT to create a verifiable instruction corresponding to a specific persona, and then you take the output directly as a prompt that you then pass back into another model to generate a completion. So it's pretty simple, and it changed our workflow substantially. But at the end of the day, we get this kind of big distribution of data sets, and I have a comparison on the next slide, but it's just kind of interesting to see where the length is. So over time, the context length of these models has increased a good amount, but most of the training data that we're using is still 2,000 tokens or less. I think our final run will be on an 8,000 context length, but most of our training ablations are at 2,000 to 4,000 context length, just because of the increased cost in compute and scaling to longer context on just those few samples in the batch. And that's kind of the comparison that we do. I was just kind of interested in Tulu 1 and Tulu 2, which are older SFT data sets, definitely had shorter context length, and the distribution is definitely less Gaussian, while as a popular other open data set, Open Hermes, is shorter context, but the distribution is really smooth. No definitive answers on if the distribution is actually that important to the models. It just makes sense with respect to stable training to have a diversity of training or diversity of input data. Nothing complicated. An important thing that we found when training these, which is now actually very public, takes this Unsloth AI blog post and Hugging Face's follow-up, is that we were using this what we called a sum loss rather than a mean loss implementation in Hugging Face training because of this gradient accumulation bug. So if you don't know about this, essentially there was a bug in Hugging Face impacting a lot of the instruction training code bases where the samples in the batch were not being weighted proportionately due to how you were counting padding tokens in a batch with gradient accumulation. So we had found that we avoided this. This Unsloth AI blog post is really great at summarizing it, but this can be like a 1 to 3 point average performance across your eval suite just by this kind of one implementation trick and gradient accumulation being wrong. So there's a lot of, it's almost like there's a lot more gotchas along the way of training these models than there is like really specific implementation tricks. So it's like the implementation tricks are avoiding losses rather than specific gains. Now we're going to kind of do the same walkthrough for preference fine-tuning, and I'm kind of holding the actual numbers to the end as a kind of carrot to make people keep watching to see where we got to. But this process is very similar. I think there's kind of one key change, which I've pointed to. So there's kind of big questions in my mind looking at preference tuning starting this project is like, why is ultra feedback so good? I think there's multiple ways to argue this. There's the idea that just like LLM as a judge is really good. But there's also the idea that ultra feedback has about 15 models completions in it. So the preference pairs that you end up with are going to be close to most models that you're training. That's kind of what I thought, is that we're like taking a spray and pray approach and we're getting some preference data on almost every model that gives positive signal. But by making ultra feedback more specific to the models that we are training, we could probably get higher performance. But there's also simple questions of like, why is ultra feedback still state of the art? Like, why is this data set from a year ago still performing some of the strongest performance on these like multitask benchmarks? Do we need on-policy data like these Llama and Nematron papers that we showed before? And kind of a goal that we got through some advising is like, how do we balance our SFT flop budget to our preference flop budget? It's like, if we think this is a valuable learning signal, we should be using a lot more computation at that stage just to kind of actually validate this hypothesis. So there's been a very big imbalance there, which we haven't fully solved, but that was kind of the goal to address. The kind of this is the figure from the ultra feedback paper, and what they did seems very similar to what Tulu has done. They took instructions from a wide variety of datasets, popular chat datasets or other specific capabilities, and then they take a bunch of models and they generate completions and they do different types of LLM as a judge. It's clear that a lot of diversity was a very important aspect to ultra feedback, and I still think that's a big reason as why it was successful. But we kind of need to focus into ways to make this pipeline more useful for specific model training. So what we kind of thought about this is like expanding the ultra feedback pipeline. We don't know our fancy name for it yet, but generally we wanted to bring prompts in that match our SFT distribution. And we also want to bring in this idea of on-policy data. So the prompt distribution is hard, so we don't have a final answer yet whether or not bringing in prompts from our kind of leftover SFT mix or from bringing in prompts from things like wild chat or this general chat domain is actually more useful. But it is clear that using this idea of on-policy data is a multi-evaluation improvement where you can kind of get clear signal across many training runs that it's better. So what this looks like is generally just adding our SFT models. So we call this, we keep version numbers. So it's like adding our final SFT checkpoint to the ultra feedback pool. So it is not the only model that we're generating data for, but just adding this 1 or 2 SFT checkpoints to the ultra feedback pool was a clear improvement on how we actually can get better preference tuning. But it's not clear on how to scale this up. We don't have a clear answer if we double the size or quadruple the size of ultra feedback, if we can keep getting more performance, kind of like we can at SFT. If you were to tell me that I only had 100,000 instruction prompts, I think we would lose at least half of the performance gains we see at instruction tuning. but at preference tuning, it's nothing like this. A good example of where preference tuning is particularly useful is with IF-eval. IF-eval is this kind of thing where there's a normal prompt, but there's a constraint that's like, you must answer in 3 paragraphs, or in this case on the right, it's the entire output should be wrapped in the JSON format. We saw this eval look pretty much solved with Llama 3.1 report, with Nematron. These models get between 80 and 90 on IF-eval. Nematron talks about using specific prompts where the constraints from the evaluation are added to kind of this human data that they have. And we actually take a very similar thing. You'd end up with, you create training data with very specific constraints. So the chosen of your preference data follows the constraint. It could be like, write me a poem, a normal chat prompt. And the rejected is a separate completion that is not told to follow the constraint. There's a very simple data setup, and you just get immediate boosts on IF-eval. I would say that if you were paying more attention than I ever do in these talks on our kind of test suite, is we're building a subset of IF-eval with new constraints that we came up with, because we're really curious to see if this kind of constrained, really obvious data construction that boosts the val scores immediately actually generalizes to new constraints. So I'm kind of interested to get that final number comparing our models to Llama models on this kind of generalized new IF-eval test set. If you look at preference data, it's actually shorter context than instructions, but this is not too surprising, mostly because the ecosystem around preference data is much less mature. We don't really know if we should be expanding turns to kind of use longer multi-turn preferences. We don't really have as easy of a job of getting preference signal on really long context problems, like complicated math problems where the answer is a long chain of thought, or on kind of code where the input prompt can be really long, but we don't have models to differentiate that well. So it's harder to create long context preference pairs. And I still see this as a big opportunity, but it's not that clear if LLM as a judge will solve this. It's not that clear how closed labs are getting their preferences for complicated tasks. I think just talking about this, it's coming back to me that the Llama 3 report, like 80% of their preferences is actually general chat data. So I think we have a lot of kind of hills to climb, so to say, just by using this kind of simpler preference data and not worrying about this kind of long tail of domains. So there's a lot of implementation details, kind of like the last one. We ended up using length constrained DPO, which is actually in the original DPO GitHub, and the SimPO paper from Princeton, I think, was the one that explored that in more detail. And it's funny how you converge on these recipes that work more. It's still the original DPO loss, but with just a different constraint on the number of tokens. And we train for one epoch. These things are probably going to vary through recipe, but there's a basic implementation trick where you cache the log probs of the reference model. If you're trying to scale DPO to 70 billion parameters, you almost definitely need to do this. You can get in touch, or you can see our PR. So all of our code for this project has been public, even though a lot of the other details are not. But essentially in DPO, you have the reference model and the policy model that you're learning from. Because the reference model is static, you can generate all the forward passes on that ahead of time, and then you do the policy model and kind of update it over time. This mostly reduces the memory that you need by about 50%. So that could be the difference between being able to train a 70 billion parameter model at all and not. But if you don't do this at 70 dB, you're going to need like 16 nodes of H100s just to fit it in memory, which is just ridiculous. So you definitely want to add these kind of nice quality of life improvements when doing preference training. This is probably the most fun part of the talk. I think I haven't gotten interrupted with questions, so I'm kind of assuming that this is all just plugging away well. The story behind this is that after I've always been trying to talk with John Schulman, is kind of an idol in this area. I've seen him a few times, and we got some advising from him, which is nice. And essentially the advice that he gave was to just train on the train set where you have answers. And we begun this exploration of what we have called ground truth reinforcement learning in the context of these general models. And it is remarkable how quickly this kind of caught on. I think if you say that we were told to do this a month ago. Within 10 days, we had kind of positive signal. So this is one of those things where it's like, we're going to drop this paper, and I think a lot of people are just going to be doing it. But it's also like, this could have happened 8 months ago. Like all we had to do is have somebody try this pretty specific setup, and it would have worked. So I'm going to kind of walk through what this means in the context of standard RLHF, and then I'll throw a bunch of numbers at you for results and do discussion. So if you look at standard RLHF, I think especially for a language model, this isn't general to any RL agent. It kind of looks like this, where you have the agent, which is the language model and a lot of other stuff. It takes in some prompts. It gives a completion, which goes to a reward model. And then the reward model gives some signal to the agent, which it then updates its parameters. You can expand this, and this is what the details look like. An agent actually has a generating policy, which is the policy that's getting changed over time. It has the reference policy for KL constraints. It has the value model, which the actual RL update is based on. And then the reward model is separate. It's like the environment in this case. So this is what we start with. And the kind of question is, what if we change from just a reward model to also like these reward functions? So the answer, the kind of implementation that we use is literally the simple, which is if you do some extraction on a train set, you give a reward of 1 if it is correct and 0 otherwise. And kind of natural starting point is like, oh, let's add this to the reward model. It makes sense to keep RLHF similar. But we found that this actually didn't work as well. The model just didn't learn as well. And what we do to change the implementation is we don't use a reward model at all, but we initialize the value model from an SFT checkpoint to kind of give the per token attribution kind of just like a warm start. And then when we do this, we find that it pretty much works, and we get boosts on something. If we train on something like GSM8K train, we get boosts on GSM8K train and also math. So it's kind of nicely generalizes and doesn't destroy the model, where we get these boosts and it isn't too complicated. We've done it at 8 and 7 dB already. But yeah, this is kind of how we summarize it. It's just like, we just use a reward function. There's no reward model. We keep all the PPO infrastructure the same. But in some ways, it's remarkably simple. And I think there's a ton to learn here. We have a long list of ablations that we want to run on kind of what should the value model start with? How should you balance your prompts? How does the setting compare to standard RLHF? For example, we find the kind of KL situation to be very, very low. I think for our most successful runs, the KL, when we're doing this kind of GSM8K training, which is our most useful one, the KL is only like 1 or 2. Whereas if you're doing a standard RLHF run, you can get into 10s or 20s of KL distance from your policy across the batch. And this is really easy to saturate, but as I said, we're going to have a report that has some details, but I expect this to kind of quickly balloon into a whole new area of kind of post-training research, kind of like we saw with DPO balloon, because it works on 7B kind of out of the box and the code is already out there. So it's almost surprising, where it's like, you just train on the train set and you can get generalization to similar evaluations without a ton of degradation. I think we even saw one example where at 70 billion parameters, normally the best practice for supervised fine-tuning, instruction tuning, is you drop the learning rate of training by about a half. And we didn't do this on our SFT checkpoint, so we trained a 70B model that was like a little broken. Some of the evals like MMLU or PopQA, which are normally robust, were dropping. And when you see these pre-training evals particularly drop in post-training, it normally means that you're training a model that's just kind of like it's just in a bad loss phase. But we took this kind of broken SFT model and threw 70B PPO at it, and it kind of brought up all these broken evals back to a normal baseline. And this was like, is still one of our highest eval models to date. So there are a lot of very weird things and very promising things in this, and I'm excited to kind of bring this to more detail to more people pretty soon. I'm going to breeze through some results. I think this will probably be something that people ask questions about because it's just a lot of numbers. I think at 8B, our previous benchmark, which is nice to have, is Tulu 2. We put these on the left. I put these on the left for most of these plots to see how, if we take this Tulu 2 recipe on Llama 3 and apply it, where do we stand relative to where we are today? So you can see the Tulu 2 recipe is easily surpassed by Tulu 3, and then kind of we have these big gains through SFT, and then small gains of DPO, and then small gains through this RL stage. And there are some evals where we're ahead of Llama. There are some where we're behind. I think math is the focus. So we're always trying to get exactly the same math on a slightly different eval setup than the Llama 3 paper uses. They use a really specific prompt and this kind of Minerva formatting template. in their evals, and we're using a more flexible extraction, mostly because when you compare to other models, switching the slide here, you can see we tried to compare to models like Gemma 2 Instruct, News Hermes 3, which is trained on Llama 3, Quen 2.57b, the new Mistral AP model. Just to try to do fair evaluations here, we use a more flexible math eval. So the big result for us is to just have a model that clears Llama 3 Instruct on average across our task suite that we started with. And we're still trying to push these numbers higher, and some evals are easier than others. I think Alpaca-Eval is fun to throw in here because you get these outlier numbers where some models are just crazy high on Alpaca-Eval, but their actual average score, if you include more reasoning tasks, tends to be a bit lower. What this looks like in a table is this. This is the same information. Mostly include this for potential questions, and then after the fact, if people want access to the slides, they'll let me know. And we do the similar thing at 70B. 70B is much newer. We've been trying to train 70B models for a week or two. It's very recent. We have a similar thing where we barely cross the line on our best models. We're yet to figure out the sequencing of DPO and RL at 70B. We're just kind of seeing at the beginning of the stages, but we're in a decent path to start. Similar when you compare to things like the new Nematron Llama 70B model that they trained from Instruct, which is crazy on Alpaca-Eval. There's some degradations on other evals, which let us beat that on average. Similar thing with Hermes 3 as a good baseline versus from base, and then those kind of Quen models. Another table that I don't need to let you stare at. 405B, we hope to train for the new year, but we have to change our recipe because like we can't do PPO at 405B, so that's not going to be part of this, just based on how much memory it would take in training. I'm going to kind of breeze through some interesting points as I'm getting towards the end of the time that I said. It's just there's so much here that this is kind of like extracting things that I found interesting from what is a giant project and a lot of moving parts. For kind of a ballpark, and this is what maybe some people got drawn in from when I shared on social again that I was doing this, is that we trained about 1,000 models, maybe towards 1,500 when we're actually doing this project. We have a leaderboard where we keep all the results of all of our intermediate checkpoints and like automatic evaluations and things like this. But it's just kind of nice to have a ballpark for like how much compute does it take to create a recipe that is like the best that you can do at that model checkpoint. We're getting to the point where a lot of our evaluations are saturating. So like if we have a really good DPO model, it's really hard to get the model to go up more with RL. Whereas if you had a bad SFT model and then you do RL on it, you can get much bigger gains. So especially at this like 8B scale, there's a lot of evals that saturate in like in math and really hard things like this. We have a team of about 10 to 15 where it's been most people's primary focus. I mean, people go submit other papers, do normal things for about 3 to 4 months, just as again, just because it's good to share this stuff. And we're experimenting with DPO, but we're going to try PPO kind of with this Tulu 2.5 paper to see if we get this 1-point boost at the end. There's other things we got boosts for, like on our final SFT model, we got a 0.5 point by doing basic souping. So if you train 3 SFT models and then do a naive merge with them, on average, we were getting about 0.5 point. And these are the little things that are like annoying. It doesn't feel very academic, but it helps us most of the time. We found a lot of evaluation contamination in popular open datasets. One of the things that we're going to release is just mirrors of these datasets with the exact prompts that were contaminated removed. So if you look at things like ShareGPT or LMSys, there's a lot of exact Alpaca-Eval prompts in there, even with truth, and same thing for truthful QA. Like NVIDIA's Daring Airteater dataset we found to be really helpful on math, but the kind of open source prompts that they pulled in had contamination. Our own like kind of safety training mix had violations on safety evals. I think a lot of this just kind of is very hard to track. So you kind of have to, decontamination happens at every step of the way. So like every time we have a new SFT version, the person who leads decontamination comes in and be like, these prompts were not, they were in our test set, so we have to remove them. It's kind of a constant process and not one that you can just do at the very end. Otherwise, you can have a lot of headaches. Something that one of the colleagues is doing is trying to boost our MMLU scores because we don't like being behind an MMLU all the time. So the way that we tested this was that if you take MMLU, it is just a test set, but you can artificially split it into a train and test set. And then if you take the base model, you can train on your artificial train set and you can train on your artificial test set and then test the accuracy on that artificial test set only. So what we're seeing is that if you train on a set of MMOU prompts that you're not testing on, you don't actually get improvements. So it seems like that in order to get improvements on MMOU, you need to have very specific knowledge corresponding to the test set. And then when you train on the actual test set, the numbers that you get are very similar to what some of these top MMOU Instruct model scores are. So I won't say definitively whether or not people trained on test, but like these types of experiments make it hard to not be cynical of models that aren't releasing their training data. Some conclusions and kind of hopefully motivations for people interested to latch on to things in the space. I spent a lot of time in the last few weeks thinking about incremental post-training, which was largely my motivation for this work, versus this kind of distillation from large models. And in reality, I think we have a really substantial shortcut from being able to distill from models like GPT-4o and train on those outputs. Whereas I don't know if there will ever be the academic motivations to actually do this like 4 or 5 round preference collection where you have new prompts and you do LLM as a judge and you slowly push out the frontier of the model over a lot of retraining, which is like that Llama 3.1 figure that is my biggest motivation behind this. I don't think we'll ever, like, I don't know if we'll ever be able to get a huge ecosystem around this, but doing some research there will be really, really important. And it's something that I want to do more of in 2025, which is just like, if we have an Olmo model, what is the best post-training we can do with only like a certain type of model? So only with like Olmo models, how far can we go? And I think we'll need to scale up to bigger models with Olmo at pre-training in order to kind of bring these instruction benefits into this long scale, into this kind of whole ecosystem, which is why Llama 405B was probably very important to Meta, who cannot take the legal risk of training on OpenAI outputs. Also, I think we just have a lot more work to continue building preference data sets and recipes around preference tuning. I think within leading a team here, it's very easy and intuitive to study instruction data and just kind of make it work and keep hill climbing on it. So that's kind of a safe space to go to, which is like, oh, I'll keep doing instruction data. That's where like, that's what we've done. It keeps working. Like building new SFT data really works, but I still think that there's bigger opportunities and doing impactful work in preferences. So that's kind of where I would end, is like making new data is very effective. So just relying on mixing or whatever small preference data sets are out there is like, do not take that as a given. And if you're interested in a certain area, like just really make more data sets, and that'll kind of how the whole community moves forward. So we're going to release a lot of things. I think we're going to release all the data sets that I mentioned earlier on for kind of instructions and preferences. We'll release a bunch of checkpoints for different models. I think I didn't share numbers for Olmo models in this slide deck because the numbers for Olmo models are not done. We're also going to have decontamination code, eval code, and all the likes. So you can email me if you're very desperate to know exactly when that is coming, when I know it is, but it should be pretty easy to know when it actually comes because AI2 will push the narrative, and it's very exciting to all of us that are here. And this would not be possible without a very involved and strong team of people. I tried to arrange them alphabetically here just because there's a lot of different roles, and people from PYIs before grad school to senior professors. There's a lot of types of things that go into making a project like this work. So thanks for having me, and I'm happy to answer questions.
Hey Nathan, thank you so much for this talk. I think it was really interesting for us to be able to see kind of what went into making the next generation of alignment techniques. And so I'll just jump right in. Some of our questions are maybe a bit dense, but I wanted to start by asking, so you talked a little bit about the importance of decontaminating the validation set. But there is, in some sense, a contamination that's very subtle and insidious that can happen, where maybe you look at your GSM 8K score and you say, okay, like I want this score to be better, And then you say, okay, I'm going to generate some more examples. How do you stop yourself from falling into the trap where maybe like on a surface form, you start copying the benchmark, or maybe on like some, deeper latent features, like maybe you're not considering the full set of operations that might be considered? Because ultimately, you kind of don't want to shoot yourself in the foot by making GSM-8K now be a benchmark that doesn't accurately reflect how your model is going to do on unseen math problems.
Yeah, that's what I was trying to get at is like a lot of this story is going to be defined by what our like validation test scores are. So if the like our held out test scores are good relative to Llama and peer models, that means that like some of these claims about diversity and generalization are probably true. But if they are look awful, that means that like we did that. And that's why like part of the fun of it is to try to, it's like we ultimately will have ownership with whether or not like how much you should focus on evals. I think um, I generally think that there aren't a lot of people that do the amount of vibes tests that they do in academia, and like spinning up demos is important. But I think academics are really good at hill climbing on evals. That's like what AI, that's what these Tulu models have been really good at in the past. And like I don't have a good answer. I think it'll just be a reality check and kind of show people like this is this is how it ends up. But this is why like doing a principled approach is good. So I don't have a good answer, which is just wait and see. But I agree, which is why like in some way making a diverse eval suite is important, so it should help counteract that to some degree. But like we're submitting, I need to do this today, it's like we're submitting a preview model to LMSys where we want to, and we're gonna like that's another val test is like what is the LMSys score. But I think just using the models is important, and you have to get to a certain caliber of model before people actually like to use their own models a lot, and we're starting to cross that.
Yeah, I think that makes sense, and we're kind of looking forward to seeing the polished results. So I think a lot, maybe the part you were most excited to talk about was the ground truth RL or GTRL portion. And as I understand it, and a couple of audience members also asked similar questions, GTRL is a little bit related to STAR, where you're essentially performing RL on data that you could have essentially SFT'd on, except the only difference is now you've got the model generating it and you have this ground truth reward, like you know what the correct answer would be. And if that's correct, then does it suffer from a similar problem where if we're in the domain outside of math or code or some place where we can deterministically say that this is the correct answer, we don't actually know how to do like an analogous procedure to GTRL?
Yeah, that's definitely the case. I think at the highest level, it is another conundrum of like where generative AI is good and where it is not. So generative AI is really powerful in domains where you have a verifier, which is like why math and code has gotten so good. Like we haven't done code, but we want to do code. Code's just really hard to implement. But like this is why the models are getting so good at all these things is because there is this verifier. But we don't know how to scale this to arbitrary things. It's like IF-eval is an interesting one where we have implemented instruction following, like precise instruction following, which because you can evaluate a string based on a Python function. And we have done that as well. But it's like, how many of these domains can we create this kind of evaluator for? And I don't have a general answer, but I agree. And I think people figuring that out or working very hard there and like having some proxy that actually works in general use will be very impactful.
Okay, yeah. And so to follow up on this question, I kind of wondered, to what extent do you think the benefit of ground truth RL over learning from human preference is due to the fact that human preferences are inherently noisy, meaning like you won't get this 0-1 reward. And in fact, the formulation of DPO, etc., requires the Bradley-Terry assumption, which means that you definitely don't have this 0 and 1 kind of binary preference. And so do you think that if we were to develop better ways to deal with that noise, model that noise, we might be able to get human preference learning to kind of be as useful as ground truth RL, or where do you stand on that?
I would believe it. I think you're in like the fundamental limit. I agree, and it's a fun question. I think I mean, you can tell obviously both where I explicitly said it and I didn't explicitly say it is that we like had a meeting with John Schulman where he's like we could advise. Well, he like wanted to help advise open recipes for RLHF, so I think that he obviously wants this knowledge to be shared. It's like his pithy way of saying it is like humans are high noise, low bias, and LLMs are like low noise, high bias. And I think it's like we just need to figure out how to use humans for what they are good at and like in the right domains. But like we also don't have the money to do humans that well in most academic labs. So that's why I think like LLM as a judge is a good field because it's like it's obvious that people are going to do it because we don't have enough like human annotation budget. But in the limit, I do think you'd be able to guide humans to do this. It just involves by getting very specialized humans and paying them enough so that they're willing to do the math problem. It's like doing a math problem that's so hard. Like I don't like doing random GSM-8K prompts for your job for $20 an hour sounds extremely hard. But fundamentally, I don't think there's a limiter on the like a signal that you would be learning from.
Yeah, thanks. And here's a follow-up, kind of a broader version of our first question. So what do you see as the ultimate goal of RHF preference tuning? For example, do you think it might be possible to replace RLHF given all these like difficulty and like good quality human preferences, stuff like that, with simply just high quality SFT data or high quality curated like ground truth RL data as well? So you talk a little bit about trying to mesh this budget invested into the both phases, but would love to hear a little bit more on how you think about these trade-offs and do you think one might be replaced down the line?
Yeah, so I think preference tuning mostly is about style control and kind of behavior control. And it is a contrastive loss function. So I think for some domains, that's just a better signal. And that is what most of these labs are doing. I think like there's the table in the Llama 3 report, or both of them is interesting, where you compare the distribution of SFT to preferences. And I think when you're doing SFT and preferences, that is true, but it also is like other RL things on ground truth signals like math and code are, I don't think they're going to be replaced soon with SFT. I mean, A, based on how easy it was for us to do this, and B, like how good some of these models are getting at coding. I do believe that a lot of that is from figuring out how to do this well, and this being like RLHF and post-training, because it's just code is like, I guess for example, like an anecdote from the RL training is it's fun to have these models side by side where you have like the DPO checkpoint and the RL checkpoint just after it. And you could definitely see that it is changing kind of how it is reasoning and how it is behaving in chain of thought. Whereas getting that exactly right with SFT is just really hard. So I'm kind of a believer in that it's just like it is a more flexible loss function. You could see it change behavior in kind of like ways that we wouldn't come up with. And therefore, I expect it to keep working, kind of irrespective of all the noises from industry, which is like, oh, post-training is driving all the developments and stuff like this. And on one hand, they obviously care about chatbot arena scores as they go up and up and up, but there are other things that actually deliver meaningful value on the code side. So I don't know. It's a balance, but I do think that SFT is not the only thing. And this is the argument that I have, not an argument, but kind of a spiel that I have to give a lot of times to people. Like I do think SFT is really easy and we aren't done with SFT. So it's like nice to make progress on, but it's just kind of this kind of soft blanket that lulls you in and you spend 2 months mixing SFT data again. You're like, where did my months go?
Yeah, I think that makes sense. It's nice to hear your perspective on that. And so I guess I have a question that's more related to your thought process while you were working on Tulu 3. So when you undertake kind of this systematic study of alignment, I think one of the crucial questions is like, what evaluation are you going to be using during your iterations on the method or the data or so on, to tell yourself that, you're getting some positive progress. And I guess there's some, underlying dissatisfaction with Alpaca-Eval, and things like that. And so I kind of wonder how you approach this. Like, if you could, in some sense, open source your development process, that would be really interesting, I think.
Yeah, that's definitely what we want to try to do. Like there's this draft section in the paper that's like philosophy, and it's like, what are we doing here? And I try to understand this. And that's like why Alpaca-Eval is like one thing in our Val suite. We have found with like especially in this Tulu 2.5 work, we find that like if you just run PPO more, like Alpaca-Eval keeps going up and up and up, and eventually the other evals just start going down. And it's like the model with the highest Alpaca-Eval for us was often not one that we actually enjoyed talking to as much. And like for the average user, it probably is because these things roughly are correlated with chatbot arena. So in some ways, it's just like choosing our eval suite based on behaviors that we want. But I do think the kind of story of being slightly too fit to them is a kind of important tale. And there's little things like we have a safety eval, but we don't really feel like we want 99 on a safety eval because that's just pushing the model away from, you have like distributions of like academicness, which is like your eval scores and like who your users are and like who you are. And you do this like rough match where they don't fully align. But in reality, like different team members have different amounts of caring about this. So I think there are some people that just look at the eval scores and then a few people that are like want the model to be good. And that's not everyone. And it's hard to balance all of the approaches. So I don't think there isn't that clear of a way to distill it, but it is very messy. And I think that's just kind of as you have somewhat moving goalposts, it's expected to be messy.
I see. Yeah, that makes sense. And I guess like zooming out a bit more beyond these kind of capability focused evaluations that you were talking about, I kind of wonder like how do you gain confidence about what the behavior of the model would be under arbitrary or potentially adversarial prompts? And that can be like, I'm asking it a math question, or that can be like I'm trying to jailbreak it. So I guess there's this huge spectrum of prompts that I could ask it. And so I wonder like you kind of talked a little bit about this, but I would love to hear more about how you weight these different possibilities.
Yeah, so I think you just need to play with it. I think mostly we're like 80% plus is on the RVals, and then there's like a long tail of things we like. We include the Aya data set blatantly because we know a lot of chatbot arena is multilingual. So like we want to have some multilingual in there, which is like it didn't make evals go up and it didn't make evals go down, but we're like, oh, we'll keep it in there for LMSys. And then another data set, which is Coco Not, which is an AI2 project on like understanding non-compliance as opposed to just safety. And it's an SFT data set, but even for things like just jamming the keyboard at the model, it really makes the model much better at being like, oh, it seems like you entered a random sequence of words. Like, did you mean anything? Whereas if you look at some of our older models and you go to them, they just break. It's just like endless stream of emojis or something like this. And that's just like one, I don't know, 20,000 prompt data set, which is probably not all of the behavior of it being better. I think wild chat type stuff probably has things like that in that because it is distilled from GPT-4. But in some ways that there are like kind of mental mappings that you could make to the data set. But you need to play with these things. I think I just leave a couple of GPUs that have VLM servers with our basic like Gradio wrapper where you can do side by sides. And it's like, oh, Llama versus us. And like you just when somebody adds a code data set, you ask about code or something like this. And just kind of like, does it make rough sense? It would be better to have human annotators doing human eval with their versions and kind of do an internal mapping, which I'm sure these labs all do, and ranking these things on different tasks, but we don't have the money for it. Or we might, but we don't have the motivation to spend the money in that area.
Yeah, that makes sense. And earlier in your slides, you mentioned that we haven't made much progress without distillation from these existing large models. So I was wondering, do you anticipate this type of approach to keep scaling to the future? And some audience were also wondering, do you anticipate any legal concerns around distilling from large models, especially proprietary models like GPT output, stuff like that?
Yeah, I mean, this was more of a discussion last year, and I don't speak for my entire legal department, but this is definitely something that AI2 talks about, which is like, it's obvious that you could train on outputs that other people have released, but I think the TLDR of the licensing idea is we don't actually apply like a restrictive license we don't license the data because we don't think that the outputs from AI models are like copyrightable or anything like this. So the license that when we release these outputs is like ODC by or whatever, which essentially says like you as a user are responsible to look at the license of the subsequent artifacts. But in this case, the subsequent artifacts are AI outputs. And therefore, it is like recommended to understand the terms of use where our models are released for research purposes, and we are not trying to build a competitor with ChatGPT, which is what the terms of service often say. I think in the case of Llama models, it's much more restrictive. So when we release our Tulu models on Llama, it'll be Llama-Tulu3, whatever. Like that is in the license, and we cannot get around that. So there's much more legal gray area for models like OpenAI or like GPT-4 and Claude, where it is plausible that you can trade on them and kind of not have huge repercussions, or you kind of word it in a specific way for your audience. But for Llama, it's like you're locked in. I think we've weaved in and out of using Llama 405B for completions in this project. So we had data sets along the way. I think we kind of a random list of like VN SFT and preference data sets that we'll release configs for. And like one or two of them are like Llama 3 Tulu V 3.5 preview mix. And it's like, okay, we hope that's not the one, but you kind of have to follow the rules there. But the kind of back on track is like, this is also something that closed labs are doing. Like they're using Claude Opus to train their smaller models. Like it's also important to them. So I do think in some ways it is mapped. It would just be nice to have clearer understanding of like what benefit comes from where and how to actually do this in a sustainable way.
Yeah, that's great to hear the insight of like how you kind of went in and out of using these models and how you think about it. So, yeah, with that, I guess we will wrap up the session. Thank you again, Nathan, for the really great talk. We're excited about the preview. And just for everyone watching, we're not going to release the recording until the paper and associated assets are released. And so you're lucky if you tuned in live, you got to see it a few weeks ahead of time. But yeah, thank you again, Nathan. And we hope you had fun with us.
Yeah, it was fun. Thanks for dealing with the rough draft. You can definitely track me down and email me if you're urgent. There's a lot of fun discussions going on.
Great. Yeah. So yeah, with that, I think we can go off the live stream.
Thank you.
All right, we're